Okay, this module here is going to work through the way that I think is the best for getting your head around the big compound heart cycle diagram. Now, at first glance, this is a pretty intense figure because it's got kind of a lot of moving parts. Um, but don't panic yet. There are some, I think, what I think are relatively simple rules that we start from, and we can then kind of backtrack our way to explaining all the events that we see. So I recommend that, and if you're following along at home with the figure that I handed out in class, this I think would be helpful to be able to mark up, and I'll post that on Blackboard as well, so you can, print up your own if you need one. Now, the pressure part of this graph is really the one to start with because we must remember throughout this that blood always moves from where it's in high pressure to where it's in low pressure. When you're reading this graph, all of the panels are aligned relative to the time. So though you can't see any labels in this snippet of it, it's starting from an arbitrary point in the cardiac cycle, and time is proceeding to the right. This particular panel is showing you the pressure, obviously, going from 0 millimeters of mercury up to 120. So notice here we see traces for the left atrium, for the left ventricle, and for the aorta. So we're looking on the left heart only. There is a similar shaped graph you would see if we looked at the right heart, but we'd see that all the pressures are a little bit lower because, the pressures, the pulmonary circuit's a shorter circuit. Okay, so check it out. During this early phase here, notice that the pressure in the atrium is slightly higher than the pressure in the ventricle. So what happens is, during this period of time, blood is going from the atrium into the ventricle. Just passively, because the pressure is just a little bit higher. This period of time we would call ventricular diastole. Diastole is a word that means filling. Okay, the very end of this period of time is this little kick of muscle contraction that's called atrial systole. Systole is the word for when a chamber is contracting. Usually when we talk about systole and diastole, we're specifically referring to the ventricle, but we can use those terms when we talk about the atria as well. Now, notice here, when this color change happens, this is when the pressure of the ventricle is now higher than the pressure of the atrium. So now, so as the ventricle contracts, goes up, eventually it just exceeds and just skids over the pressure in the aorta. Then, when the ventricle relaxes, it goes back. The pressure goes down, and then it kind of hangs out down below the atrial pressure again. So you notice this graph probably starts over again at about here. So we're seeing like a heartbeat and a third or so on this whole graph. Okay, so that's the first thing. Notice during this, like the blue regions of this, the atrial pressure is higher than the ventricular pressure. The orange in the middle is where the ventricular pressure is higher than the atrium. Okay, so let's now lay some more information on this. During the same period of time, we're going to add on to this panel that's showing the volume of the ventricle. Okay, this particular book doesn't show you the volume of the atrium, but that's okay. We can reason our way back to that. Okay, so check it out. During the period of time when the atrial pressure is higher than the ventricular pressure, blood is going from the atrium into the ventricle. And that is reflected here where we see the ventricular volume kind of gradually going up. Then there's this last little kick here for atrial systole, so that shows like this little bump in the curve here. So as the ventricle is filling up, but then once the ventricle starts contracting and the pressure goes up, there's like this no man's land here. See, there's like a flat line. This flat line here is called the end diastolic volume. It's showing the maximum volume of the ventricle at the end of its diastole, the end of its period of filling. All right? But during this period of time, notice that the ventricular pressure is higher than the atrium, but it can't go back because remember that the left atrioventricular valve is closed, right? So because we talked about in class how the pressure from the blood will close valves. Anyway, but then in this period of time, we see, the pressure is increasing in the ventricle, but no blood is going anywhere. This period of time, we're going to call later isovolumetric contraction, which means the same volume contraction. Okay, so that period is happening there. But now here, when you have a slight color change again, this is when the ventricular pressure is now higher than the aortic pressure. So so now blood starts to leave the ventricle down here. So from your end diastolic volume, and it'll continue to get ejected into the aorta until here when the pressure lines cross again. So at the very bottom here, if this was EDV, end diastolic volume, this is the end systolic volume. That tells you the pressure of the volume that's left over in the ventricle at the end of its systole, at the end of its period of active contraction. But at this point, at the end of the ventricle's contraction, notice the pressure is now lower than the atrium again, so blood can now start passively going in. So again, you coming, the kind of the slow creep up of the ventricular volume. That happens just because the atrium's been filling up with blood from the vena cava and the coronary sinus. So blood's going to go where it wants to, down its pressure gradient, and then the cycle continues. So again, some points we can label here. At this point, when the ventricular pressure is higher than the atrial pressure, that's when you close the AV valve. And actually, there's this little bump here that comes as kind of the reverb of the contraction of the ventricle, but sensed inside the atrium. In here, there's this no man's land. This period of isovolumetric contraction where the pressure's going up but the blood's not going anywhere because the aortic semilunar valve hasn't opened up yet. Once it does open and it kind of starts to eject the blood out, you get this stroke volume, the amount of blood that's ejected during this period of ventricular systole. Now here, as the pressure is starting to go down again, I should say here's where the semilunar valve closes, but it doesn't just close, it like slams shut. So it's a much bigger like reverb you see. It's a structure that feature that we call the dicrotic notch. So that's like the slamming closed of the semilunar valve. Then here, when the left ventricle is relaxing, but there's no blood going anywhere, as you can see from the end systolic volume, we call this the period of isovolumetric relaxation. And then again here, you start once ventricular systole starts again, that's when you get this kind of progressive filling up of the ventricle just passively until that last kick that happens at atrial systole. Okay, so these two together will kind of explain, we can see the changes in pressure, and now we can overlay what's happening with the valves and the movement of blood with this additional panel. Okay, now how do we control these? We saw in the last module that this P part of the ECG, that is going to start the atrial systole. So this P just precedes the contraction of the atrium. Then this QRS happens when the ventricle is depolarizing, and as it depolarizes, it contracts, so the pressure goes up. And then the T wave, this is where the ventricle is repolarizing. So see, repolarizing and like also relaxing around that period of time. And then it continues along to the next P. So the ECG comes first. The ECG causes the changes in pressure because it causes the contraction of the myocardium. And then, so the ECG causes the pressure changes. The pressure changes is what cause the movements of blood. Okay. Now, the heart sounds. So there are two sounds. The first one is called the lub sound, and that happens around the time that comes due to the closure of the AV valves. And then the dup, the stronger second heart sound, is the slamming closed of the semilunar valve that happens here at the dicrotic notch. The reason why it slams, whereas we say this one just sort of closes down here, the AV valve, is because the pressure is a lot higher. See, this one closes at about, 15 millimeters of mercury, but it but this one closes at, say, about 100 millimeters of mercury. So one other thing about pressure, we can relate the aortic pressure to our systemic blood pressure. You probably have heard before that a healthy person's blood pressure is in the ballpark of 120 over 80. Now, what those numbers mean is that when those numbers are the systolic pressure of the aorta over the diastolic pressure of the aorta. So the systolic pressure is the pressure in the aorta when the ventricle is contracting. And the diastolic pressure is the pressure in the aorta when the left ventricle is filling, during its diastole. So check it out. This is the end of ventricular diastole, and the pressure in the aorta is about 80. This is the pressure of the aorta at the peak of its systole, which is, just under 120 here. So this would represent, maybe not 120 over 80, but at least, like, say, 115 over 78 or something. So this 120 over 80, we measure in the periphery by, say, measuring whether it's the carotid artery or the subclavian or however it's measured, measured down the arm on the brachial artery. So that kind of maps onto this we're looking at as well. Now, at the bottom of this figure, where they're showing what the condition of these valves is, you don't even need this really. What you should do, in fact, what you should practice is remembering basically what's causing the heart sounds, and you should be able to reason whether a particular valve is open or closed. The phases, yes, the phases have names, but honestly, from my part, the most important things are for you to be able to relate the ECG with causing pressure, the pressure with moving blood, and also the pressure with causing the heart sounds as well. So when you look at this whole thing, you can see that there's this period. Each of these different phases, has a name hung on it, and it'll kind of show where the blood's moving around during that particular period of time. But again, I think you can do that based on kind of starting with the basics, with pressure first, then the blood volumes, then the electrocardiogram and heart sounds, and then the rest of this I think you can reason your way to. Okay, we'll clean this up in class, but this is the way that I've found students who have the most success to learn it. The other thing they do is they don't just look at pictures. They also draw this stuff out. This is one of my first teaching assistants, Michelle, who spent time in the old anatomy lab just drawing this out by hand. And don't get me wrong, she didn't trace this, she copied this. She copied this from the book, but there's something about drawing it for yourself that makes you really see it in a way that's different than if you just look at it on paper. So you don't have to create some great work of art, but it's getting there through the work of your hand is really what's going to help you to learn this the best way. Okay, that's it. I'll see you in class.